What is up, everybody? Welcome back to my channel. This is Tony, aka One Leet One Day. If you're new here, this channel does one leet code per day, following the pattern of topics or series. That is, I'm going to be solving with you together on a leet code problem I have never attempted before. You heard that right. There is no prescripted answer. We're on the same page here. But don't you worry, I got you covered, and I promise that I will submit at least an average performance code at the end of each video. Here's a little bit about myself. I come from a non-computer science background, so I'm no better off than most, if not all of you guys, in terms of coding knowledge. But that is okay. If I can do it, you can do it. It is all about learning on the go. You can think of this video as a first-person gameplay of cracking leet codes. And who doesn't like first-person gameplays, right? So without further ado, let's start today's coding problem. Today we continue on Series 1, Everything About Dynamic Programming, and the problem is number 55, Jump Game. So let's get into it. All right, 55 Jump Game Medium. It's one of those original leet codes because the numbers is small. You're given an integer array in nums. You are initially positioned at the array's first index, okay? And each element in the array represents your maximum jump length at that position. What does that mean? We'll figure that out. Return true if you can reach the last index, or false otherwise. All right, let's take a look at an example. If we have input of nums of 2, 3, 1, 1, 4, right? So it is not necessarily an ascending order of numbers, and output is true. So what does that mean? Explanation. Jump one step from index 0 to 1. Okay, if you jump from the index 0 to 1, okay, then 3 steps to the last index, 1, 2, 3. Okay, so I see you're stepping on 2, 3, and 4, and you consider that a success. All right, let's take another example, 2. If nums is 3, 2, 1, 0, 4, this is false. Explanation, you will always arrive at index 3 no matter what. Its maximum jump length is 0, which makes it impossible to reach the last next. Oh, this is like a sinkhole that you can never go past. Why is that? Well, I don't know. I don't know. So let's read the description again. You're given an integer array nums. You are initially positioned at the array's first index. In this case, it's 2. In this case, it's 3, right? And each element in the array represents your maximum, okay, maximum jump length at a position. So you can have an option of jump a smaller number of steps, but the maximum is specified right as the element uh, of those array in that array. So in the first at index 0, excuse me, at index 0, you can jump maximum 2 steps. That means you can go from 2 to 3, you can go from 2 to 1. You have those two options. And then if you did arrive at index 1, you have 3 options. You can jump 1 step, 2 step, or 3 step. Which if you jump 3 steps, it directly leads you to the end. Yeah, got it. All right, so yeah, that's why the explanation says jump 1 step from index 0 to 1, and you arrive at index 1, which gives you maximally 3 steps, and you take it, and you're at the last step, and you're at the last index. Yeah. All right. Example 2. This one, why is this one impossible? Um, at at the beginning, you can jump as much as 3 steps. If you take the maximum, you jump into this zero value, which is like a sinkhole, um, and you never get out of it again. Um, uh, right, right. Or you can jump to 1 step, which could get you to 2, but still you cannot go past this number 0 here. Or if you go to 1, you still cannot go past this 0 value here. So that's why this is false. Okay, I think we understood uh, the problem definition now. And here are some constraints. So the length of the list can go from 1 to 10,000. Right. So if there's only one element in that array, you automatically reach the last index, right? If it's 1, you automatically pass. And the values can go from 0 to a large 100,000. Well, 100,000 is a pretty large value in there. It gives you almost infinite power, right? So, so if you find some number that can cover, the remainder of the steps, then you're done, right? Because you can simply just, you know, use the available jumps that you're given, you just jump directly to the end, right? But now, because we're working on, the dynamic programming series, we always wonder if this problem can be abstracted and broken down into smaller subproblems, and we can solve a complex problem by solving a simpler subproblems. And we really need to be careful and try to make this abstraction or generalization as elegant as possible so that later on when it comes to coding, it'll be it'll save us much more trouble and time if we have an elegant um, abstraction or yeah, generalization. So how shall we generalize the sub problems? I mean, because this problem looks pretty sequential. We start from like an initial position and then we just move on. It's pretty sequential in the case, I guess, in the sense that no matter how many steps you jump, uh, as long as you haven't reached the end, you're still gonna have to solve the remaining problems. Yeah, so it is kind of natural to, I guess, truncate or cut the problem just anywhere in the array, uh, and that would break the latter part, the part on the right hand side, into break that into a sub problem that you still have to solve. You still have to solve. Um, you still have to solve if, um, for example, this is a sub problem that you still have to solve if uh, if the previous steps have landed you on this number here, right? So I am going to just take this problem as an example, and then we're going to start doing some sketches. So I'm going to do sketch.io, right? This is where I usually do my sketches, sketchpad, and here we go. Uh, we're going to use black first, and we're going to just paste this problem here, right? So this is like example 1. And let's just give ourselves some space here to work on. Anyway, um, so speaking of subproblems, I may want to use a different color like red or green. Let's use green here. So for subproblem, well, green is not a good contrast against the background, so I'm gonna use this purplish color. Yeah. In terms of subproblems, for example, um, if we did jump one step from 2 to this 1 here, then we land at the subproblem of this. Right? That is if we take this jump, then we still have to solve the remaining thing because this last index is always our goal, no matter what, right? So if we take, yeah, how do we represent this subproblem? We need to, you know, let's say subproblem, use capital S to represent subproblem, and we kind of like need an index to describe which subproblem we're talking about. Like, we could take this subproblem, we could take this subproblem, we could take this subproblem, or like the entire original problem as a subproblem, right? So I guess a good way to represent the subproblem is to use the index at the start. Um, in terms of the original array. So this one would be 0, 1, 2. This will be S2, right? Yeah. Uh, and if we just think about, let's just use another color. If we're talking about this, then this would be S1 because the starting index uh, would be index 1. So these are the subproblems, and we can jump into these subproblems by making decisions earlier on in the list. So I think this is naturally a way to describe it. Uh, and of course, the original problem, let's say the original problem, what color am I going to use? Yeah, I can use yellow. So this is the original problem, which is S0, that we're going to solve. So can we say that S0, uh, it somehow equals to, because we want to make sure that we exhaust all the possible actions uh, starting from that state, initial state in that problem, right? So we start at index 0 and we can jump 1 or 2 steps. So those are the options that we have. Um, we can write, um, take jump 1, right? So this becomes S1, and then what? Plus, yeah, let me just write it kind of like in a straight line. S1 plus what? Plus, well, I'm gonna use color matching S1, right? And then we can add that with um, S2, right? Yeah, I think so because you know what? This would mean that you have taken, jump jump one, jump one step, and this one is jump two steps, jump two steps. And those are all the options that you have given the number two here. Um, so this is like a one-step recursion for the subproblems. However, we have a problem because the number of terms to add on the right, it depends on the value here at the index uh, indicated in this parenthesis. So because the value here is 2, right? So you have two elements on the right to be added together. If you have 3 here, then you're going to have 3 terms. And that is not a very, sustainable way of generalizing things because you don't want your expression of the recursion relationship to change every time with the value um, of the value of the first element in the subproblem. We don't want that to change. So is there another way to, I guess, generalize the problem without having to change the expression on the right hand side each time? Again, we need to sit back and try to generalize this in a better way. Because this equation that we have come up with right now, it is kind of like intuitive. Maybe 70-80% of people when they first attack this problem, I'm just guessing, they would come to the same expression that I have. But it's not necessarily a good one or a sustainable one to stand, the iterations because again, the number of terms on the right hand side depends on the value of the first list element in the subproblem, and that is actually a problem, right? So, and also if the value of the first element in the subproblem, if the value is greater than the length of the problem, then we can just say, okay, we found the solution. We can just directly jump to the end of it. We only need to work on subproblems when the fir- uh, the first element value isn't large enough. That it doesn't go directly to the end. That is when we still need to break problems down, right? That's true. That's kind of true. Um, and also because we cannot travel backwards, you can only jump forward, right? So that is kind of a limitation. So now, can we maybe run this in a different way? I'm just thinking, can we be a little bit of a innovative and thinking out of the box here? And what if, let's just say, what if we start from the last element and go backwards? I don't mean that we jump backwards, but we just think in a backward uh, fashion. So let's say we have the following argument. If the second last element is greater or greater or equal to 1, then we're done. Like, then we don't have to worry about these two, because if we can reach the first one, we can reach the last one. Yeah. And similarly, if this element, this uh, second to last, the third to last element is greater or equal to 2, then we're done for the last three. Or if this element is greater or equal to 3, excuse me, we're done for the last four. Yep. Because the nature of this, it's like it has a radius. So yeah, radius. I think the key word is to think it as like a radius. Although it only projects forward, you can just call it forward radius, right? Forward radius. This 2 means that it can cover the forward radius like this. And the 3, that means you can cover an even larger forward radius. Yeah, so this is like the forward radius of 2, right? And 3, this is even more powerful because that means it can cover all the way up to the end. Right, so that's the forward radius. So, right, as long as you can, you know, use your forward radius to reach uh, an element that to reach an element and reach an element and eventually to reach the last element, then you got this covered, right? So with this forward radius kind of like analogy, uh, um, right, we can we can build it from the back and just build these forward radii and we can basically solve the problem. Yeah. So for example, if I start from the second to last, and this forward radius only covers that much, it's not good enough. And this is the same, like it just covers the next element. It's not a big one, but this one is a big one. Like it covers them all. It's a pretty big forward radius. Uh, and then when it comes to this number here, well, you realize then it covers 2, but that's good enough. That's good enough. Yeah. So if we use this like forward radius as a way of abstraction, then the problem of solving, I guess, S0, if we use the same notation as previously, well, let's just put a line here to mark the boundary between our first intuition and now the second intuition. So S0, uh, whether it's a true or a false, it depends on whether the forward radius of this first element covers, right, so we're doing some coloring, okay? Right, we need to, yeah, that's the point. Like we need to do coloring. So for the first, um, right, and we're gonna use like solid color to mean any forward radius that can, reach the end. So this is one, and the second one it does not. It actually it is one as well. Wait, yeah, because we've already colored this one, we've painted this one like solid or filled. So if we can reach a filled region, then this region is also, you can also fill this. Like it's almost like a spread of paint, right? Like if you can reach the paint, you get the paint. And this number three here, um, well, there are multiple ways this element can get the paint. You can just go to the next and get the paint, or you can just jump maximum step, maximum effort. Use your maximum effort and jump to the end and get the paint. So I'm gonna like use the maximum effort and it will get the paint. And really we should really first try the maximum effort to see if it gets the paint, because the paint kind of like spreads from the last element backward, to the earlier elements. So to just make the computation faster, um, you should just first use your maximum effort to see if you can get painted, right? So it's like, yeah, it's like contamination. Uh, and in this case, the contamination is a good thing. So we're just gonna use the word painted, right? And then number three is painted. Uh, and then number two, now it'll also be painted because you can reach three and three is painted. So I think now we can come up with like a way of computation, or um, a heuristic for computing stuff. Now let's use black. Right. So I'm thinking we can do this bottom up to spread the paint, right? Like, yeah, the idea is to spread the paint, you know, bottom up. So this is our approach, and we combine this, spreading paint idea with this forward radius idea. So work on the last element first. First, this is like our nums list, and this one has 1, 2, 3, 4, 5 elements, right? 5 elements, 5 elements. Uh, so we're gonna start from S, meaning subproblem, um, of what? Um, of the last one. Well, the last one you don't really need to do it, right? S4 is automatically painted because it paints itself. It's the last element. So we start from S3, uh, and we look at its value, and we take the maximum effort, right? Uh, take maximum effort, take maximum effort, right? Uh, and we see if it kind of like gets painted, gets painted, or um, or not. So take the max effort. It jumps to S4, it jumps to the last element, index 4. So yes, it gets painted. Because it gets painted, we're gonna say S3 is is true, right? S3 is true because true means it's painted. Logical element. And then we work on S2, which is this element here. Uh, Again, we take the maximum effort. We take the maximum effort, which is jump one step, um, and see where it gets us. It gets to as it gets to the subproblem of x3, right? Or like it reached the state uh, of index 3, and because we know s3 is true, so s2 is true as well. All right, so s1, um, again we do our max effort because s1 is this guy. It's at sub value of 3, and if we take the maximum effort, we'll jump 3 steps. We'll reach s 4, which is automatically true, right? And then lastly, we look at S1, S0, and let's just use our maximum effort, okay? Because once we found something that is true or painted, we just stop. We don't have to, use, less effort and try again. Max effort, this gets us to, uh, because you can jump 2 steps, you become arriving at S2, and because S2 is also true, right? Because S2 is true, we knew that from previously. So this is true. And this is our computation. It looks like we do need a storage of O of n, right? Yeah, um, and in terms of computation steps, I think it's also kind of like O of n. So space complexity O of n, time complexity O of n, right? So this is our algorithm. And before we implement it, we just want to maybe make it more abstract, find a general expression for it. So this one on the left, we're not using this, right? Yeah. Let's say we are not using not using this. We're gonna use this. Whoops. Yeah. Use this. Right. Uh, we want like a more general expression. Let's use a new sheet and write it down. So our more general expression, if we write it, it's going to be, let's try black. So eventually we want to calculate this S0. And let's say our nums list has n elements. Okay. Um, so it starts from, yeah, and nums, right? Let's say nums 0 all the way to nums of n minus 1. That's our total number of elements. And then, okay, oops, this is really big. And then we can start, we start the subproblem, start with the subproblem of s, well, m minus 2, right? Yeah. So what is Sn minus 2? So Sn minus 2, whether it's true or false, we're going to take the maximum effort. And the maximum effort means that we're going to take uh, the element, right? So we're going to take the element, uh, and if this, if we, after taking the maximum effort, it gets into like a painted region, right? If it gets us into the painted region, we're good, right? Right. And then we're gonna do s n minus 3 maximal effort, right? Again, if the maximal effort, which is Sn minus n minus 3, gets us into the painted region, we're good, right? Otherwise, right, otherwise, uh, otherwise try a lesser effort. Yeah, try a lesser effort and see if it gets us into the painted region. Right, right, and we're gonna iterate. Right. Uh, let's see, what can we do about this? We can actually make it look not that annoying by doing this. Right, right. So we better demonstrate using drawing here. What do we mean by that, right? So this means subproblem. Let's make it more general. What if it's the right? So iterate and we go all the way down to a arbitrary subproblem of sk, and the maximum effort would be to look up n of k, and then we jump that much, right? And we're gonna jump to uh probably jump to which element? Jump to index uh, k plus nk. Uh, and then we look at, you know, we look at whether S of that k plus nk is um, is a painted region, right? Um, so painted region, if we go back to this, it's just like this. We have a forward radius. If forward radius is all that we can, is all the places we can cover, Um, right. And so, um, um, right, right. So I think we're almost there. I'm just thinking maybe we're missing a little bit of something because I was worried about, the case where we have this example of two, where you have a zero here, like a sinkhole in the middle. Um, so you definitely, um, the painted region kind of stops here, and you cannot go past this place. So, so there's no painted region in this case, right? Yeah. So anyway, I think we're good. I think we're good, and but you can never be too careful at the generalization stage because the generalization stage means everything. If you generalize it good, you can probably wrap up the code in terms of you can probably just wrap up the code in 5-10 minutes. Yeah, or 15 at maximum. So if maximum effort gets us into the painted region, we're good. Right, right, right. And that's SK. Whew. And what if, look at that, right? So we haven't finished this entire sequence yet. Let's finish it. Look at that. And, if, so if S of K plus NK is true, right? Is true, we need to look no further than SK is true. Return, right? We can basically say return SK as true. Um, otherwise, else, we're gonna do the max minus one effort, meaning we're gonna take uh, nk plus one. That means we jump to index uh, k plus nk, whoops, k plus nk minus one, and then we're gonna follow that again. Uh, so we can basically use this as a while loop, right? So this can be a while loop. Um, and if if none of these efforts can get us into uh, a a um, a painted region, right? If we've tried everything, then we're gonna return sk as false. So this is basically our recursive relationship in terms of looking up um, the subproblem value of sk. And and intuitively, let's just try to understand this thing a little bit more intuitive again. So let's say we have this k value, right? We have this k plus one, whatnot, dot dot dot, and we have finally, of course, we have this n minus one as our last element, and we have n minus two, n minus 3, like that. Um, so we're gonna basically start from here and look up its value, right? So we have this nk here, and we take this nk and then, just use maximum effort, jump, 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 jump here. Let's say we jumped to a value here, um, and this is what k plus k plus nk. Yeah, k plus nk. And we see if this k plus nk, if it's already painted, if it's in the painted region, right? Um, and when we say painted region, let's actually paint it uh, with red or orange. Excuse me. Yeah. So the last one is by default painted. N minus 2, who knows? Let's just say, just make the case here. Let's actually make an example here. If this one here is actually value 0, then definitely we cannot paint this because it's a sinkhole and we don't get past that. But if we have a number 3 here, just for example, it's a number 3 here, then what we can say is that because we have a number 3, uh, and the maximum effort can actually get us past the sinkhole and get there. So we can say that, this is definitely a painted region, right? Um, and what about this problem here? This problem of s, I guess m minus 3. This subproblem, is it true? Yes, it is true. So that would mean, the whole idea of this. So we can basically say, hey, this whole thing is painted. And we can just, carry the sinkhole with us because it is fine, right? Um, is it? Well, what if like the only option we have from upstream are like numbers of ones and ones and ones, and we have a 2 here, meaning we're gonna jump into the sinkhole, right? We have a 2 just before this 3 here, and we're gonna, jump from this 2 into the sinkhole. Would that be a trouble? Of course not, because why? Because we don't have to jump 2 steps. We can just jump 1 step to this number 3 here, and we will automatically, take the best solution within this problem, and that will carry us to the end. Right, so I am convinced that a sinkhole in the middle of a subproblem is not a problem at all, as long as we can find a solution starting from the first element in a subproblem. We're good. Because if you can reach the sinkhole, that means you can reach the element before the sinkhole. That is no problem. So, all right, I think we got it this time. Um, we have again this is our you know, whoops. This is our, let's say, this is our DP recursive expression, right? That's our DP recursive expression, and we're gonna just use this to solve our problem. Now let's just go back to coding. Go to coding, uh, and copy the problem description um, into our notebook and start solving it. right? We have an example. Great. And we're going to copy the solution template and start coding. So this is going to be simple. We know that, we need to store um, all like n values of our subproblems. And that is going to be a space complexity of n. And we're going to perform up to n steps of this calculation of sk, which is again not a problem at all. So we would do that, right? So we need to define another member function as a function to look up the the subproblems. Yeah, let's just do that. Define subproblem. Let's call it sub, right? And we need to give it, in like in first, right? First and first. Yeah, that means that the index of the first element would mark which subproblem it is, and we're gonna say int first is an integer and return type is bool. Yep. So how do we do that? Now, if we go back to our intuition here, um, we're gonna first look up the max effort, right? We need to look up the max effort. Um, look up the maximal effort possible. And that would require us to actually um, read the list value. Um, but we don't have it. We only have an index here. But what we really needed is, I guess we needed, in this process we need to read in k from k. Uh, we also need an access to s as well. So that means we need to build a storage. And for storage, I can use, if we use lookup, the most efficient way is to use a dictionary, right? Uh, yes. So we're gonna define a dictionary. S uh, is going to be an empty dictionary. We're gonna say to store calculated subproblem. Yep. So this will look like, you know, something like, for example, in example one, it'll store 0, 1, 2, 3, 4. Well, yeah, 4 is of course true, right? And 3 is true. You know, just as an example, it'll look something like this. Yeah, initialize. Initialize the dictionary, and then And then we are going to basically return sub 0, right? And then sub 0, well, yeah, if you initialize, I'm gonna have to say, right, so n equals to the length of nums. And then the first element, it would be n minus 1, uh, and true. Is that how you initialize dictionaries? Let's look it up. Python initialize dictionary. DICT. Or you do this, yeah. I think we're right. We just initialize first element in dictionary. Yeah, and then we can crank the recursive function like this. Uh, and we're gonna look up the maximum effort possible at that index, right? So we're gonna have to look up the value in there. Nums, um, nums of in the first, but we don't seem to have nums here. So we may have to send nums in as an element. So that means type of nums will become list of int. I start to feel that we don't really need this, but yeah, let's just do it first. Let's see if we can optimize the code. Look up the maximum effort possible. So this is the maximum effort possible. And once we have the maximum effort, we jump using the maximum effort and see where we get, right? And also, overall, this should be like a while loop, right? While while we still have options. So while effort is still greater than 0, and we need to initialize the effort, right? So effort equals to nums. Yeah, we're gonna initialize it as the maximum effort. So this is the maximum effort. And then while we have not exhausted our possible efforts, we're gonna, do something. And then we're gonna reduce our effort, reduce effort by 1. Right. So reduce effort by 1 is effort uh, like that, right? Okay. What is do something? Do something means we want to look at the state where we jumped into. So self dot, we just look up this as dictionary, right? And we're gonna use the current index, index plus the effort and see where we arrive at. And yeah, we're gonna see if it's true or not. if this is true, we break, right? We break the while loop, um, or we just return. How about that? We will just return true. Um, and if not, we're gonna do this, right? Yeah, you're gonna reduce our effort by 1 and we do it again. Right, I think that's it. I think that's it. Like we initialize this and then we return something, and this function is going to crank start the recursive relationship. Uh, and uh, and yeah, what about the return false condition? Because by default, um, yeah, if we have exhausted all the efforts, right, then we have to return false. If we tried all the efforts above 0, yep, it's gonna be returning false. All right, so let's try this with the test cases. So for test cases, we're gonna take the test cases from the problems themselves, but we're gonna use the same syntax. We steal the syntax from before, build a solution. This is what can jump. Uh, and we're gonna take these test cases. The first one is gonna give us true, right? And we're gonna do another one. This one is gonna give us false, supposedly, and we will try it. All right, let's give this a try. Okay, got some error. Okay, sub is not defined. Right, oh right. We always forgot to use the self prefix for member functions. All right, a solution object has no attribute s. Well, yeah. Well, what is it? Print return self sub self s. What is this? Key error 2. I don't know what this key error 2 means. Let's look it up. Python key error 2. What does that mean? Dictionary key error 2. Dictionary key error 2. In order to set a general default value for all keys, you can use default keys, default dict. You're telling me it has something to do with the default key value. Um, oh, because we have not found a way to update the dictionary, right? We forgot to update the dictionary. Yeah, that's that's me bad. Like we are doing recursion, but we're not storing. We're not using memory basically. That's why when you try to look up, you cannot find it, right? This is like look up the state, uh, by applying effort, So you have to store it, right? So before you return true, uh, you want to update this. Use which key? Use end first, and then say this is true as well. This is just update s, right? Um, and if everything has been tried, um, do we update like a subproblem as false? Mm, yeah, I mean, if the first element is, for example, like a 0, then it's uh then it's definitely a dead end, and we're gonna have to update that uh, 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 subproblem as a false. And first equals to false, update as. So, right, we have just added, 2 lines of updating the dictionary either as true or false, depending on whether it could be painted or not. And I think we're here. I think so. Let's try. But still, we have this key error of 2. Now let's start debugging, okay? Let's use the debugger and see why it gives me the key error of 2. And it's on line number 20. Okay, let's take a look. Here, self.s is a dictionary, and then length is 1, right? So what is index first? That's 0, and effort is 2, and 0 plus 2, that is going to be 2. Oh, okay. Because we have not stored anything here yet, all right? We have not stored anything here yet. Right, that's why. So going back, I think what you have just implemented is a top-down approach, but what you wrote here is, yeah, this is like a top-down approach with memory. But then, the thing is, you do not have a memory yet. You did not have a memory for S2 yet when you are trying to call it. Um, right. So because this does not exist, um, the key does not exist. uh, You're gonna have to uh, you're gonna have you're gonna have to make it exist first. So let's do that. We're gonna do C if ind1 st plus effort is in self.s.key right? Is that keys or keys? Python dictionary. Oh, keys. Keys, right. It's keys. Got it. Um, then we're gonna do that. Else, this is gonna be like a recursion. Well, let's put this in there. This one belonged there. Um, yeah, else we're going to have to work on we're gonna have to work on it. We're gonna have to um, return um, sub. Yeah, this is gonna be a little bit tricky because how do you, if you didn't have that value, um, of course you're gonna have to work on finding the value at that index first. And the way you do it is you return sub of mm, I mean, if we can have that in keys, we don't need to perform that lookup, perform the calculation for it. But if we don't have it, right, I got it. Okay, so I think this is the order of doing things. Um, do nothing. So not in. Right, if it's not in, mm, self.s, we want to update it, right? Um, we want to calculate it first. Equals sub. Uh, yeah, this and nums. So what this does is to, you know, calculate the landing subproblem if not yet available. Problem solution value if not yet available, right? So this means if we do not have, in this case, uh, s2 stored in our dictionaries, then we have to calculate that s2 first using the same subfunction in a recursive fashion. So now it becomes calculating sub 2 nums, and it will look up that over again. And once we've looked up that, we come back to uh, come back to, yeah, the DP recursive relationship. Yeah, this is a little bit tricky than I thought, but we'll get used to it. Bingo. There we go. Okay, so I think we just did a hot fix. Um, actually, a reasonable fix to the problem. And now we have a solution. Let's run the code. It runs. This also runs. So let's potentially submit. Okay. Again, special case is 0. We're expecting true, right? So in your test case, always remember to include a special case because you can always expect Leetcode to have special cases. So now it's going to return false, but we want it to return true because, yeah, if there's only one element, that is, if this is like one element list and would be 1, um, right. So if n equals to 1, we simply return true. Yep, that is a hotfix. Run code. Submit. Wrong answer. List index out of range. Okay, that's a pretty good feedback. Let's try that again. Let's try using that and see what do we expect. Do we expect true? Yes, we expect true. Okay, so what went wrong? Effort equals to nums index list. The maximum effort possible. List index out of range. List index out of range. Okay, let's actually use the debugger and find out what is wrong. All right. And now we don't need these cases. We just need the last case. Well, I mean, that's what I was looking for. Oh, it's line 19. Okay. All right, let's restart the kernel. Make sure the debugger runs properly. All right. And then we're gonna turn on the debugger, put the debugger on line 19, run this line, and run this line here. So right now our nums list is 2 and 1, 2 and 0. It's got a length of 2, and in 1 in the first, it's 0. So uh, this effort is gonna probably give us effort of 2, right? So yeah, effort of 2. Let's move on. Now we're at what? Um, int list 2. Wow. Oh, we are. So the maximum effort, if it like, yeah, that's the thing we haven't figured out. If the maximum effort is like exceeding the length of the remaining subproblem, we just directly return true. All right. Yes. we're gonna we're gonna add a condition here. If end first plus effort is greater than the length of the subproblem. What does that mean? Um, Subprob length. Yeah, if it's greater than that, we directly return true because you can jump to the moon like you can jump to the end, right? And how do we calculate subproblem length? Well, um, subproblem length. Yeah, let's use this visualization here. So subproblem length, for example, in this case, um, yeah, we want to be able to do like a subproblem length calculation, right? Subproblem length. Give me 1 second. This is probably just one last thing we need to fill in here. Um, yeah, subproblem length. A general expression for that. Um, we could use the total number of elements in nums, right? Minus uh, right minus the index for the subproblem. What is that going to get us? Um, index k. In this case, it's m minus 3, right? So it's going to be m minus m plus 3, so it's going to be 3. Exactly. So m minus m minus 3, so it becomes 3. Yeah, and that's exactly how much length we have. So we're going to use that intuition. Length of nums uh, minus end first. Right. So that's the length of it. And if the first index plus effort, right? If the first index plus effort, which is like the landing state index, is for example, int first plus effort. Oh, okay, because this is already in the indices for in the nums list. So actually, we only need to put lens here. Yeah, we don't need to calculate the subproblems. It's just the length nums, actually, -1, greater or equal to, actually. Yeah. So what do we mean here? We mean if the maximum effort is large enough to carry us to the end, the last index. We just return true, right? Right. So that is what I mean by that. And let's try that. Yep, now it returns true. And let's try our remaining test cases. True, false, true, true. Yep, right. So kind of a little tricky, huh? We have a few uh, edge cases here. And we just have to make sure that those edge cases are taken care of. And we submit. Seems like it's working. Down the test cases. That's promising. Ooh, time limit exceeded. That's pretty bad, right? Because, wow, that is a pretty long list. And you're basically telling me that my computation is not efficient enough. Okay. My computation is not efficient enough. Well, for this, how do we compute this fast? Like, we first simply check if this actually, projects us directly to the end of it, right? This seems to be like a test case where you go down from 10,000, right? Uh, and this one will probably give us like a maximum effort leap all the way down to somewhere here, like on number 3, number 2, or number 1. And we will see if that is like a legit case or not. Well, we can jump here and we can jump from here to here as well. But these two sinkholes is going to stop everything, stop any possibility from happening. So this is going to return false. But if you use the top-down approach instead of the bottom-up approach, you're going to be computing forever. And you're going to never get over the last two zeros. Hey, so this is a really, really tricky test case, huh? It's a tricky test case in that it stops the top-down approaches pretty quickly. Uh, for this problem, bottom-up approaches would be good because, um, well, if it's bottom-up, we start from the last element. This is an impossibility, 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 and all the way, these are like impossible, impossible, impossibles, impossibles, and we build it up, right? And it's probably just gonna take linear. No, yeah, it's gonna be O of n in terms of computation steps, which is still acceptable. But the way I did it in a top-down approach, and it's gonna try a lot of efforts. Okay, it's probably gonna try a lot of efforts. Right. Well, uh, let's just submit it again. See if we can skip this special test case and get somewhere. Doesn't seem like it. Seems like we have to deal with it. Yeah, every time you throw me this test case, and it's gonna run forever. I know. This sucks, but you know what? I'm gonna take it. I'm gonna take it, and I'm gonna use this test case. Tricky test case. Uh, right. S equal to solution. We just want to print, let's say S can jump. This is nums. Yeah, big nums. Big nums equals to this. Yep, it's a very big array. And it's going to be tricky. I mean, if we just take the last two zeros off, I think we can easily return true, right? It's going to take no time. But if we just put one more zero here, it's also fine. I mean, it's just going to take no time and return true. Yeah, but if we add two zeros at the end, that's where things quickly gets ugly, and it'll take all the time there to tell you that, it's a false. I don't even know how long this is going to take, but it's really taking a very long time. It's got 10,000. It's got 10,000 values in it, and it's definitely exceeding the time constraints for the Leetcode submission. So I'm stopping it here, not running it. Uh, we definitely have to uh, fight this tricky test case. And how do we do that? Well, by our design of this top-down approach, unfortunately, it's a top-down plus memory, right? So uh, unfortunately, we won't be able to reduce or optimize. I think uh, if we do bottom up, that computation can still take quite a bit of a time. So yeah, this really bites me, huh? Yeah, this test case really bites me. Let me just take a look at this forward radius intuition and see how can we deal with that problem. Let's just, you know, make a very special case for it. Yeah, it's a really tricky case, right? So we're going to really use something 9997, right? 9996 dot dot dot, and then you have 321 and two zeros there. Pretty much. Pretty much. Okay, so this is the tricky case. The problem in this tricky case is the following. Yeah, let's see. We're going to use the same purplish color to do that. So if we start from the second to last and we do our uh, forward radius thing, this is like an empty. So this is not painted because you cannot get there, right? It's just like, yeah, it's stuck here by itself. Doesn't go forward. And this one here, yeah, so this one is basically like this. Doesn't go forward. This one here, it does travel forward to include the zero, but it doesn't get you to the last element either. Um, this one here has a larger radius of 2, so it will cover the next two elements, but still it doesn't get there. And then of course, number 3, it won't do that. So yeah, this is like a curse. Yeah, this is almost like a curse. Even if we use bottom-up approach, even if we use bottom-up approach, we're still going to end up looking at impossibilities and impossibilities, and it'll still take us in calculations. It'll still take us in calculations to get there. Um, yeah, in calculations, not too bad, right? Because if we have something that is like, say, uh, instead of like 9,000, let's say 20,000, right? If it's 20,000 here, then this will immediately include everything by its radius. Will be good. So you definitely don't want to give up trying until you reached all the elements in your list. So no giving up. I mean, this is probably the most efficient thing you can do. Probably. It's going to be like a bottom-up approach, right? This is going to be a bottom-up approach. All right, so what do? I think we have to try this. We have to try this bottom-up approach. Try this bottom-up approach instead. And let's see if it gets past the time limit for the Leetcode. Yeah. And what is now the recursive relationship for this new bottom-up approach? So yeah, so that means we're going to be working our SK backwards. Yeah. Let's go back to our new expression here. So yeah, let's start writing it. Fine. Fine. And we're going to start um, the procedure. We start from S of n minus 1, right? And in this case, it's going to be false. That's fine. And then next we work on S. Well, why is it false? Because, you know, we look at the value of n minus 1 equals to 0. So that's like the effort, the max effort. Max effort is 0. So you don't go anywhere. And because you don't go anywhere, it's a false, but that's fine. We're going to use ME to represent max effort later. Right. And then for S m minus 2, our maximum effort, which is n m minus 2, in this case it's 1. So we can jump one step, but then it's gonna land us at the subproblem of S m minus 2, right? And because that's false, this is still gonna be false, right? So now we try again S m minus 3. and look at our maximum effort, which is to look up the nums list, and minus 3, it is 2. So we can jump 2 steps maximally. And we look at that, jumping 2 steps gets us nowhere. Hey, you know what? Yeah, I think I just found a new intuition. Instead of looking at, maximum effort and whether it land us uh at like a if it can land us at a uh painted area region, we just look at, if the maximum effort at some, oh, wow, okay, interesting. I shouldn't be doing that. If the no outlines, okay. What have I done? No outline. Yeah, outline using this color. Fill is none. What do we say? No fill. That's not what I wanted. Zero. Yeah, 0%. Yep, that's good. So we only need to see if the maximum effort of a certain index can get us past uh, this hopeless non unpainted region, right? Like we're gonna be looking at whether this can make us leap a little bit into can make us leap a little bit into go past um, a hopeless unpainted region. Can we can we do that, right? So right, because now we're on the streak of false. Like this is like we're gonna use yeah the purple color to indicate like we're on a streak of false, 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 like no solution, no solution, no solution, no solution so far. And now let's change it to the magic color, the purple color. Let's say if this is 3, okay? If this is 3, and that is going to do our magic because a maximum effort of 3 will now be able to break the barrier uh, and get us some new stuff. So yeah, and the point is there's no point of looking at, lesser effort. There's no point of, looking into lesser effort if we were on like a streak of failure. Because if we were on like a streak of failure, uh, with no painted regions at all, we only need to try the maximum effort. And if the maximum effort does not get us anywhere, we just dump this number once and for all and go to the next one, go to this one and try it, right? So I think this is something our previous heuristic, our previous rule also missed and therefore was not efficient, which is like we were saying, hey, if we tried our maximum effort, which is a good thing, if it's true, then we're going to return this is true. But then for this else condition, we're somehow reducing our effort by 1. Like why, right? Like why would you reduce your effort? Like this is your maximum effort when you jump from k to k plus nk. Um, and and you shouldn't be, you know, looking for any effort that is less than that because, you know, for these efforts that are less than it, if the maximum effort if the maximum effort can't get you to the end, then none of the lesser effort can. Is that right? Is that right? I mean, think about it. Yeah, we have all the time here. Think about it. If the max effort cannot get you to true, then no less effort can. Is that true? Is this statement true? If the max effort, I'm going to use purple for this. If the max effort cannot get you to the true, then no lesser effort can. Is that true? So let's try to use contradiction to prove it. Um, Contradiction to prove it. So let's assume that the maximum effort cannot get you to true, but a lesser effort can. Right. Let's just see if that will lead to a contradiction. Let's use yellow here, and then let's say a lesser effort, for example, this effort, you know, by using an effort of 1, right? We'll get here. If this can actually lead to a true solution, then that means the subproblem of this is true. So this whole list between this element and the last element becomes a subproblem that is true. And if that is true, then then the maximum effort, which also jumps into this, this this true subproblem, should also be true, and that contradicts with our um, initial assumption that the max effort cannot get you to the true. So right, I think we just proved it by contradiction, right? Okay, proven by contradiction. So we should say it here that this, oops, proven by contradiction. Yeah, so this is proven by contradiction to be true. So that means what what that means is that we would never need to use less effort if the maximum effort doesn't work. So just use maximum effort and see if the resulting subproblem is true or not. Otherwise, just return false. Yeah, yeah. Okay. I think that's a great uh, you know, relevation. So we really shouldn't be doing like else, and we don't need the while loop. So this is just gonna be an if loop, and we don't need this else. So if effort is greater than 0, right? You know what? Why not? Let's say if effort equals to 0, we just return false. Um, right, I mean, we also want to update it, right? So we don't have to update it here. And right, so if effort is 0, that means the maximum effort is not getting us anywhere. It's getting us stuck, so it's definitely a false. And it means the subproblem starting from there is a false. Yeah, that's basically it. And wait, yes, right, yeah, yes, that's right. And then if the effort is actually greater than 0, basically that means else, right? Yeah. And if the index plus the effort um, has exceeded the last element, the maximum effort is large enough to carry us to the last index, we don't need to calculate further. Otherwise, we calculate the landing subproblem value if not yet available, right? Uh, and after we calculated it, we look up the state by applying the effort, maximal, applying the maximal effort, uh, and yeah, based on the landing state, if it's true, then we're gonna also say that this current subproblem is true. Otherwise, return false. Okay, uh, let's just try it with this update. And the previous test case is also passed. For this new one, yes. And it's fast enough, right? Good. I think we got it. So at least we can pass this test case. Right, let's just close these searches and let us crack this problem. Yes. Run the first few test cases and submit. Wrong answer? Oh, come on. Okay, 2500. This is supposed to be a true case. Why is that? Because number 5, this gives us, enough authority to jump to the end. Okay, that means our logic still has a problem, right? So let's add this new test case, tricky test case 2. So what are we expecting? We're expecting true, right? Yeah, and our current algorithm predicted false. Let's see what went wrong. So our algorithm would start by calculating sub-zero. But we'll first assign, uh, let's see, well, it's probably better to use, again, a drawing. So we're gonna use another drawing here for this failed test case. Good thing is the number of elements is pretty small and it's representative. So we're gonna just hand calculate uh, the calculation steps that we have in our code. So the first step in our code is that we are going to assign true to the last element inside um, inside inside the nums list. So let's do that. So we're gonna assign, yeah, so we're gonna write, basically we have an S dictionary and we're gonna assign true to this last element, right? We will have like indices, index. This is gonna be 0, 1, 2, and 3. So the first step we assigned true to the index 3 right there. Uh, yeah. And then we're trying to return self-sub. And then we go into sub, and it's going to be sub 0 in nums list. And effort is going to look up nums 0, which in our case is 2, right? That's the maximum effort. You can say this is maximum effort as well. This is also the nums list, but it's also the maximum effort. So we look up the maximum effort, and what do we do? Well, let's see if the maximum effort is equal to 0. It's not. It's equal to 2, right? So else, if index first, which is 0, plus effort, which is 2, and this equals to 2. If 2 is greater or equal to the length of nums minus 1, so the length of nums is going to be 4. 4 minus 1 is 3. So this won't be true because it does not carry us all the way to the end. It, it doesn't. So we jump to the next if. If index plus effort, which is 2, is not in self.keys, uh, right, we have not gotten an answer for that subproblem yet. So we're going to then fill that up. S2 is going to be equal to self sub of 2 and nums. So we're trying to, the next step is we're going to fill up this. Right, next step, we're gonna fill up this. And we will jump again into sub, but this time we come with a different in the first, and this time index first, it becomes 2. Nums is the same, nums. Uh, and effort, we're gonna look up the effort with the index 2. So the effort at index 2 is 0, maximum effort 0. And it is now maximum effort 0. And now we see that this goes nowhere. Yeah, uh, yeah, it does go nowhere. So we're going to basically say this is false. And that is correct. So because that is false, we now go jump out of the sub calculation and we're going to say, hey, um, we basically updated S2 to be false. And then we're going to see if self.s2 is true. In this case, it's false. Okay, so we again skip this if condition or pass this, yeah, skip this if condition. And then we're going to return false. So that's why. All right, so that's why our calculation returned as false. Okay, so what's the problem? I mean, we've walked through the code and see how it actually leads to a computation of false. Now I'm trying to see what's the loophole in the logic. So let's animate this again. We try to start at index 0, and then we see that the maximum effort is 2, right? And it's going to bring us from 0 to 2. And then we went on and calculated this as false. Um, so this is false, meaning we think that the subproblem of 2 and 3 is false. So we didn't try, you know, the one less effort here. Hmm. We didn't try that one less effort because we were saying that if the maximum effort couldn't get us to a solution, then no lesser effort can. Yeah, and we just proved that by contradiction, didn't we? And now we're basically slapping our own face, saying, "Hey, it's not right." Hmm. Uh, take a drink. All right. So this means our previous conclusion um, was wrong, and in this case, we do need to try lesser effort to see if it gives us an opportunity. Excuse me, an opportunity to go to the end. So why was us wrong here in proving that this statement here? If the max effort cannot get you to true, then the lesser effort can. Actually, lesser effort can. All right. And our contradiction was saying that hey, um, if the maximum effort cannot get you somewhere, but then a lesser effort gets you somewhere, then that means the subproblem from starting uh, from this closer uh, index is true. Like, right, and then the maximum effort should then automatically be true as well. Uh, well, I guess this comes down to our precise definition of what is a subproblem because that is so important. The definition of a subproblem is so important, and we seem to have like a very blurred definition of what a subproblem is. Right. This is a very important lesson. So let's try to start defining what is our subproblem. Um, if we define our subproblem as like a sublist from some element in the original array up to the last element in the original array. If we define our subproblem in that case, uh, and what does the true and false of that subproblem stand for? Does it stand for uh, the truth of completing the challenge if we start from the initial index, or does it stand for the truth of the problem if we start at any index in that range, right? So this is the difference. Um, and we have to choose one definition. We have to choose one definition. I think to be consistent with the problem itself, we're going to use the narrower definition. Say our subproblem only allows us to start at the first index in the subproblem. And we're going to write that down explicitly just to remind ourselves, okay? Because this is so important at the detail. Right, we can only start at the first index in a subproblem. This is consistent with the original problem. Yeah, this statement is so important. And it's so important, and we are going to stick with this from the beginning to the end. And what this means is maybe we still need this else statement to try lesser efforts. And and this is no longer true actually. Not true. This is not true. Yeah, this is not true. This is not true, so we cannot skip the lesser efforts. But then this brings us now um, back to the other more difficult challenge, which is if we have to try all these lesser efforts, yeah, if we have to try these lesser efforts, and that's a lot of efforts we need to try, right? Um, and the subproblem How many total subproblems do we have? We have n total subproblems. And once we'd stored all that n subproblems, um, once we solved all that n subproblems, um, and we look back at the first original problem, uh, you can easily look up the answer, right? True. So, I mean, now we're back at now we're back at this large problem again. Like if we add back um, the while loop, then this tricky test case 1 will take forever to run. Right. And if we cut this else condition, then it's not compatible. It's wrong. It's not compatible with our subproblem definition. So it seems like we don't have a solution here. It's either fail this case or fail that case. Uh, can we change our subproblem definition? If we change our subproblem definition to that of, say, you can start from any, yeah. If we change our subproblem definition to, say, we can start from any of the elements in the subproblem and it will still return true, then definitely that definition itself is a bad definition because what if we have like a zero there? What if we have a zero not at the end? Then it's gonna ruin the whole subproblem and make the whole subproblem like a false. And we're throwing away, the good parts. So that is again not acceptable. We have to stick with this subproblem definition here because it's consistent with the original problem. Yeah. But if we stick with this definition of subproblem, where we can only start at the first index in the subproblem, then inevitably we need to include this while loop because we have to try. Yeah, first we try the maximum effort jump, but then we also need to try the lesser effort jumps, unfortunately. But hey, can we just, I don't know, uh, if we have to use a while loop to build that, I don't know. If we have to use a while loop to build that, uh, would that be a good? Yeah, we can't seem to skip this while loop, and we can't seem to find another definition for subproblems. Uh, and so when there's like a lot of elements in the list, this search for lesser effort is going to make our computation time grow like explode. That seems to be the case. But if I was right, I mean, our time complexity should only be like what? Um, well, our time complexity Right, it's gonna be ON squared, right? Because in the worst case, if we have to try all the lesser efforts for each of the subproblems, then it's like n times n squared. The complexity is gonna be like that, right? So so yeah, that's pretty bad. Can we, instead of using this while loop and use this maximum effort, can we try to find a different way? Can we try to find a different way to solve it? How? Um, because now maximum effort doesn't really have an advantage. Right, why would you try the maximum effort? Like now, maximum effort doesn't really have a clear advantage than others. Maybe it'll save it some time because um, you need to build less memory. If your first jump happens to be like a very large jump, then and if that first jump happens to give you a solution, then you're good. But if you like your first jump is like jumping directly onto like a zero, that doesn't really help you. So maximum effort doesn't necessarily mean that it's a good effort. Okay, I'm gonna write that down. Seems like a really good relevation, right? So max effort isn't necessarily good. Yeah, maximum effort isn't necessarily good. With that being said, let's see if we can come up with a different recursive DP expression that is not based on maximum effort. Okay, let's just restart from this, okay? And we're gonna take basically what is like a useful part of this. We're gonna start from another page because we need a different heuristic. So now we know maximum effort isn't necessarily a good effort. Um, yeah, maximum effort isn't necessarily the good effort. How do we do it? Like we know we can rely on some of the subproblems in orange. Um, how do we find out whether SK, this new subproblem here, is true or false, returns true or false? Well, uh, to really find out, we have to try every effort, every possible effort, right? To really find out about that, we really need to try every effort. And don't you see, like, I guess, yeah, I think that's almost like a dead end. You still have to try every effort and then see the landing sub problem, the resulting sub problem, and then look for them. But don't you realize that, just by looking at the structure of this, you realize that most of these numbers don't really do anything because, for example, this 9992, if it's only one number larger than 9991, which is next to it, then these two guys are equally useless. It's only when, you know, this guy is at least um uh like is at least 9993. This needs to be at least 9993 to make a difference from this guy. So we can, oh yeah, so we can basically, I guess, eliminate. Right. That's a better intuition. We can basically say, going going like all of these are equally useless, right? Yeah, and then we can distill the useful ones and basically find out the useless ones. So yeah, so I guess we can have an intuition of like uselessness, like equal uselessness, right? Again, we can take this example, right? We can take this example. So 9996, right? What I mean by equal uselessness, I'm gonna say I'm gonna say that um, this one is useless, right? Useless because this one is only you know one larger than the useless one. It's equally useless, right? Equally useless. And because this one is also only plus one larger than that useless one, this is also equally useless. So we can propagate that all the way down to this and this because they're all just like plus one or less larger than this. They're all equally useless. Equally useless, right? So we can basically just, filter out all these numbers and then only deal with the useful ones. Yeah, if we can identify the useless numbers, we can save ourselves a lot more trouble. So that is probably a better, pre-treatment, This is like preconditioning. Preconditioning, right? Uh, Label all the useless indices. I think this is going to help us a lot to at least to tackle the case um, of this. So I'm going to say, yeah, uh, fill, no fill, no fill. Okay, 0%. Oh, okay, 0%. What about the fill? Yep. An outline, color, 0%. All right, so precondition, label all the useless indices. And what is the condition for useless? Um, how do you define useless? Well, um, um, let's see. Right, the useless ones are like the ones that can useless indices. So useless indices are indices that can only jump to, you know, verified useless indices, right? Indices that can only jump to verify useless indices. So if, I mean, we can verify this is useless, right? This is verified useless, and this is useless also because it can only jump to this verified useless indices. Uh, and so this is like a useless index, and uh, yeah, if this is just like one larger, um, right? If this is just one larger than that, that means it can jump to this, or it can jump to this and then do the same thing that this can do. Yeah, yeah. And it's like a chain of uselessness that we can eliminate until we find, something that is useful. Uh, right. This chain of uselessness. We want to eliminate the useless indices in a backward way. So how? Um, we can start from, the very end. Last to the very end, and we see if it's a useless one, and if it is, we can, move on and apply this criteria for finding useless indices that can only jump to verified useless indices. And what does that mean? I mean, if the if an index, right, is just if the index plus one is a useless index, then and also, right, if index plus one, for example, uh, 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 if index plus 1, the subproblem is false, right? Is useless. And also the value of that index minus the value of index plus 1, if this is less or equal to 1, then then this then this ID, then this index is equally useless. This is the expression of equally useless. So we can check this expression in a backward way for all the indices. All, but then it has to be based on like a first useless index, right? So the whole idea of preconditioning and then labeling all these useless indices is such that when we are trying our maximum effort and our other efforts, if we actually land on these useless indices, uh, we will not continue. We'll just directly assign uh, false. It's almost as if we are building up the S dictionary, or like the table, building up the table of true or false by judging whether an index is a useless index or not. Yeah. And this is just like one special rule that we found. Like if the next one is a false and the current effort, like the maximum effort of this current ID is only one value greater than the next or less. If that's the case, then we're going to say that this ID is also a useless ID. Um, but what about else? Like what if the next one is false, but this ID NID minus NID plus 1 is greater than 1? If it's greater than 1, maybe this current index is not a useless one. Well, maybe it's not, but then we will need to jump that many extra steps to find out. Oh, right. So we can save ourselves some efforts here, right? Because if if this condition if this condition that we're underscoring here, if it doesn't hold, we can still try to calculate and compute the uselessness of the current index by trying those, um, trying those extra steps, right? Right. So looks like we may be able to build some intuition based on this. So let's use this and try to build a new heuristic based on this. And we, of course, are trying to generalize things. So Let's start generalizing. We have right index. Let's say we start from k, and we have some k plus 1, k plus 2, dot dot dot, all the way to like m minus 3, m minus 2, m minus 1, which is the last one. Um, and then we have some, nums, aka maximum effort, right? So this is like n of k, n of k plus 1, n of k plus 2, dot dot dot, n of capital M minus 3, n of capital M minus 2, n of capital M minus 1. Now, uh, true or false, right? This is like the usefulness or useful, usefulness. Right. So how do we start this? Let's change to the orange color. We of course start from n minus 1, right? And it is pretty easy to determine whether this n minus 1 is true or false. Uh, let's say this one is false, because if this one is 0, it's false, right? And then we're going to try to determine if the one next to it is a true or a false. And we do that by looking at this expression here. So if SID plus 1 is false, right, that's a check. And we're going to see if NID minus NID plus 1 is less or equal to 1. Uh, so let's say, yeah, so now this is like 0. Let's say this is 2, okay? So 2 minus 0 is greater than 1. So actually, this might be useful. So we're going to then try to see what happens if you jump 2 steps. Well, if you jump 2 steps, you get to the end. Wait, hold on. Sorry about that. I think, no, this is like the last element. So we don't really mess with the last element. It is what it is. And this is like, we've already reached where we need to be. Um, so we start with this one. Let's say this is 0. So this is basically useless because it cannot jump. And then we look at m minus 3. Let's say it's got a maximum effort of 2. So now this id plus 1 as id plus 1, it's a false. And then let's write it down, all right? Let's write it down by using a black color. Yeah, we're gonna see if we're gonna create another row, whether s of id plus 1 is equal to false, whether that's true, and then additionally whether nid minus nid plus 1 is less or equal to 1. Right, and then we're gonna switch back to orange color and try to determine that, right? So for the S, right, this is the check. And then is this true? This is not true. So uh, we're gonna say useful or not is undetermined, right? Undetermined. So it's not quickly flagged as a bad one. But yeah, we're gonna use additional heuristic, additional code to determine whether it's a good one or not. So we're gonna start like maybe shooting the maximum effort and then the lesser than maximum effort, things like that. Um, so it has passed like the initial screening, right? So this means that it has passed the initial screening. Uh, and then we're gonna run basically another few lines to determine whether it's useful or not. And it turned out that it's useful. All right, so we move on. Let's actually let's actually yeah, move these things a little bit to the left because I want to try a few more examples. Yeah, just move it to the left a little bit more. And let's move these things to the right a little bit more. I just want to try a few more examples. Okay, one more. Uh, change to orange. And then let's see if n minus 4 is good or not. Okay, now let's make a case like this. It's 3. And then let's see, is the next one false? No, it's not false. And because the next one is not false, we don't need to continue with the next statement, right? Because it is not in the radar of potentially bad ones. Um, because the next one is a good one, so we don't compare um, the value of it with the value of the next one because uh, simply because it's not likely that it's a useless one. So this is undetermined. Uh, right, it's undetermined. So we may still calculate it. It turned out to be, yeah, let's actually make this a false, right? So we want to make this a false. So let's make this 2 instead. But it's just that it it passed the screening uh, of these two conditions. But because the maximum effort here is not enough, it won't be able to jump to the end. Although like the value next to it is still good. Um, doesn't really help. So now for the next, let's say now because this is a false, so if this is a 3, and because the next one is a false, we're going to trigger the first condition for suspicion. So yeah, this is like, yes, we check. And then the second one, 3 minus 2 is definitely less equal to 1, so that's a check. So we can directly flag this as off. And this is like where this uselessness check is like used, and it's gonna save us some time. We don't have to go to the next step for calculation. Right. Um, so overall, these two lines It's gonna save us some time uh, if we have like a stack of useless values next to each other. Yeah, it's gonna help us find out those ones. And we're basically going to implement this as a preconditioning case. Uh, is that right? And we're going to run this preconditioning. We're going to run this preconditioning uh, in a bottom up approach, right? In a bottom up approach. So we're going to completely reverse the way we run our DP. So instead of doing top down, we're doing bottom up. That means we instead of looking up a function, we're just going to do a for loop, right? We're just going to do a for loop. And inside the for loop, the first thing we do is we apply this uh, pre preconditioning or screening. We're going to apply this screening condition to see if this current index is like a useless index. And once it's past that pre-screening case, uh, then we're going to basically then start using the maximum effort um, the maximum effort idea that we used again before. Okay, so um, so we're going back to uh, the while loop, right? To kind of like the while loop lookup. Yeah, true. Um, so it's going to be like a for loop overall because it's a bottom up approach. We're going to just run every case from the last one up till the first one. And inside that for loop, bottom up approach, um, when checking each of the indices for usefulness, we may still have to use a while loop. Yeah, to exhaust like the maximum efforts for each of the while loop. Oh, each of the individual indices um, for its usefulness. So let's go with what? Go with that. Let's go with that. And you're talking about subproblem. Yes, our definition of the subproblem is still the same. Um, yeah, are we now using a subproblem? Let's. That's a good question. Like, do we still have a subproblem in this case? When you're doing like this kind of pre-screening and indices lookup, um, is there still like a subproblem we are using here? Because apart from being like a pre-screening or preconditioning, we are we're doing the subproblem, right? Like when we're doing these steps, like when it's undetermined after the pre-screening, we still want to use, DP. We still want to use the DP, right? To build up the problem, to build up um, the usefulness map, the usefulness table, right? Yeah. So for that kind of DP, are we still going to use the same subproblem definition that we used before? Uh, yes, we're still going to use that same subproblem that we used before, which is this one here, where we have subproblem in orange, and then we're going to use the maximum effort approach to look into subproblems. But after the pre-screening, we're gonna basically eliminate a lot of the need for some of the subproblems, and also because we're now doing it in a bottom-up approach, uh, um, we're really just looking at. We really just need to uh, look at the remaining useful ones, right? Yeah, I mean, if the resulting state is not useful, like for example, uh, we keep a list of like useful indices and useless indices, right? And we only deal with the useful indices. So that means we're gonna look up, yeah, build a useless index list. Right, that's what we're gonna do. So the preconditioning, what it does is that it's gonna build up a useless index list. So that, how is that gonna help us in the DP problem? Well, when we are doing that DP problem, um, now we can skip, we can use this useless index list to skip the ones that are useless. And that's gonna, and I think that is gonna save us some time, right? So let's bring back our submissions here, right? So supposedly this is a submission that that had this mm, maximum effort based computation. So we're gonna keep that. We're gonna keep that. But 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 this time, right? So let's just do that. But we also are going to do a pre-screening before we call this. Okay. Um, and we really do that in a, we don't just return that. Okay. Uh, we don't return that. We return self.s 0, of course, but we're going to use a for loop here. Use a for loop to do dp bottom up for loop for k in range of n minus 1. Well, we actually don't start from n minus 1, remember? We start from n minus 2. n minus 2 minus 1 all the way down to 0. Yeah. We're going to first pre-screening for usefulness, for uselessness. And if it's past that pre-screening, we're going to basically store the value of k using sub k nums. Right, we're basically gonna now calculate the truth of this index. Pre-screen this index for usefulness, and then calculate the truth of this index if it passes the pre-screening. Right. So basically we're going to use the pre-screening as an if condition here. Where's that? So the pre-screening is this. First, we see if the index next to it is useless. All right. We need to build like a useless list. Yeah. So we look that up by where we have keep a useless list. UL. Just call it UL. Yeah, I'm gonna call it UL. I'm gonna initialize it here. UL. A list of useless indices. To skip. Yep. So if how do you look up? How do you look that up? Useless. I think it's the same as that, right? Like if as self as k plus 1 is true, is like false, right? So that is basically equal to saying that it's useless. If the next one is useless, and right, so that's a check. For example, it's a useless one. Next one is useless. We're gonna then check if this condition satisfies, right? So we're gonna check if um, if nums of k minus nums of k plus 1 is less or equal to 1. If it is, then we're going to say self.s k plus k. This is basically now useless. If not, right, so this is part of the pre-screening. Right, so now we have implemented a pre-screening to quickly fill the table, the dictionary, if this is indeed the case. Right, so that'll save us some time. Right, else we're going to apply this computation, calculate the truth of the index if it passes the pre-screening. Right. This is when we actually use it. Yeah, self.sub of that. And now because of this, and because we're doing the bottom-up approach, this call to the sub function, it will be pretty quick. Right? I think so. So we're gonna do it, using the bottom-up approach all the way back to 0, and it'll be done, right? Have we initialized a few things? So we've initialized the last element as true, and then we start from the second to last index and start, this kind of pre-screening to see if that index is basically stupidly useless. I mean, this is useless. This turned out to be useless. Well, for this one, for example, the second to last one, the way to find out if it's useless is to see if the next one is useless. But since the next one is actually useful, it's true, so we're gonna actually, yeah, start with that process, and we'll go into that. We'll try the effort, and we'll build that up. Right. Okay, let's so this means we don't really need to build an extra useless index list. The use the useless the usefulness list is simply uh the S dictionary. If sk is false, then the index k is useless, right? So this is important, and this means that we don't really need to build an extra uselessness index. Right. We just said that, and let's go back to this. No, and then I think we have a code that potentially is working. Right, and it still passes all these things, which is great. Let's try this. Nice. It produced false. Let's try this. Okay. This one. Well, the great thing is we have the while loop, and we still pass this relatively quickly, which is great. But now for this, We have a little problem, but I think that's nothing we cannot solve. You're telling me that what? Um, line 15, we have a key error of 1. I don't know what key error 1 means, but I'm willing to just apply the debugger to find out in line 15. So apply that. Oops. Okay. I probably need to restart the kernel. Right. We're gonna use the debugger, line 15, and then let's apply that. What? Oh, solution is not defined. Okay. We need to define it. And previously, the error happened on line 15, which is here. And let's see why. K plus 1. Now, K is at 2. Why is K at 2? Well, because we start K at m minus 2. In our case, n is 4, so m minus 2 is 2. So we start our K as 2, and makes sense. K plus 1 is going to be 3, right? It's going to be this one. Wait, hold on. K is 2. Okay. Because we want to start at the second to last element, m minus 1 is the last element. M minus 2 is the second to last element. For S, I think we stored S3 as true. Let's see if that's right. S3 is true. So self.S3, it is true. So we then move on to calculate S2, which should return false because, yeah, I mean, that's false, right? So we go on. So now S2 should be false, right? And then now our K is at 1 because we have moved one iteration down. And then now we're going to look at if sk plus 1, which is S2, is false. Well, S2, it is false. So we move to our next line. And because maybe this time is where S2, well, S1, yeah, we're now trying to determine if S1 is false. We don't have a value for S1 yet. We're basically pre-screening it, and we're trying to see if nums k minus nums k plus 1 is less or equal to 1, but fortunately nums k here is large enough, it's 5, so we will skip this case. Now, when we come to k equal to 0, this is the best part, this is the final part, okay? So now we're looking at if self.sk plus 1, which is self.s1, whether that is false. And we don't have that yet. Oh, okay. Why don't we have it yet? S1. Uh, oh, because we didn't update it. Like that last time when we were doing S1, we said, okay, we looked up, it passed the screening. Um, yeah, so once it passed the screening, I got it. So this is the problem. So if we actually have passed the screening, right, if we pass the screening, we still need to update it because each of any any of the cases um, has to end up with an update of the value there. So I think now this works. Right, right. This works and this works. We got it. Ah, all right. This took us quite some time, guys, but again, there's a lot of learnings for today that we did it the hard way. Submission detail, and you have some failure maybe. No, here is where we submit our code. Run the code, passed, again passed. Run the code again. It's judging. It's probably looking at more test cases. All right, accepted. Ah, finally. But again, it is very slow and it uses a lot of memory. Let's just submit again to see where we're at in the ranks of solutions. Right, it's still very slow. So this time we have like a below average code, maybe because our generalization or our intuition that we came up with uh, wasn't wasn't optimal. Indeed, it's very suboptimal. Uh, but at least we have a solution. Now it's time to take a look at the solutions and see what we can learn from it. Okay, now you have what? A naming convention. We call a position in the array a good index if starting at that position we can reach the last index. Otherwise, the index is called a bad index. Right, this is consistent with our way of defining our subproblems. So if the subproblem is true, we call the subproblem the starting index of the subproblem a good index. Right, then the problem is to reduce to whether or not index 0 is a good index. Right, solution. This is a dynamic coding question. Usually solving it is a four-step process. Start with the recursive backtracking solution. Optimized by using memorization table top-down. Remove the need for recursion bottom-up. Right. Apply final tricks to reduce the time memory complexity. Right. I think we did number 3 and number 2 and number 1 just fine, but it's not optimal. So maybe number 4 is what we're missing. We don't have any tricks to reduce the time memory complexity. Okay. Yeah, because we're using this. If you remember, we're using this maximal effort uh, way to search for a possible true uh, good index, or trying to prove the subproblem is true. So maybe we're missing some final tricks to reduce the complexity. All right, let's read on. All solutions presented below produce the correct result, but they differ in runtime and memory requirement. Okay, approach one, backtracking. It's only in Java. This is the inefficient solution where we try every single jump pattern that takes us from the first possible to the position to the last. We start from the first position and jump to every index that is reachable. We repeat the process until last index is reached. When stuck, backtrack. Okay, that's like a tree search kind of thing, and it's not efficient. One quick optimization we can do for the code above is to check the next position from right to left. Right, because that means you're doing like the maximum effort first. Yeah, make the biggest jumps, make the maximum effort first. And the complexity is pretty high. Time complexity is O2 to the power of n. There are 2 to the power of n possible ways of jumping from the first position to the last, right? Because there are n steps, and if all the values are like 1 1 1s, uh, no, if all the values are like large enough, then from each point you can have mm, okay. So there's a proof of the time complexity there. Okay, but uh, bottom line, it's very high time complexity. Space complexity, recursion requires additional memory for the stack frames. Right, because you're doing a tree, so the kind of like the tree depth is how much you need to remember. Now, approach to dynamic programming top-down. Top-down dynamic programming can be thought of as optimizing backtracking. It relies on the observation that once we determine that a certain index is good or bad, the result will never change. This means that we can store the result and not need to recompute it every time. Yes? Therefore, for each position in the array, we remember whether the index is good or bad. Let's call this array memo and let its values be either one of good, bad, or unknown. The technique is called memorization. An example of a memorization table is like this. G for good, B for bad. We can see that we cannot start from indices 2, 3, or 4. Um, 1, 2, 1, 2, 3, 1, 2, 1. Yeah, these three are bad. Yeah, so these two are bad. But we can do that from indices 1, 5, and 6. Steps. We're gonna initially make them all unknown. So they're neither good or bad, they're just unknown. Um, except for the last one, which is good, trivially. Modify the backtracking algorithm such as the recursive step first checks if the index is known. Right. So the first step is to try to look up existing computations. Right. So this is that algorithm, but you still are going to use the same, I guess, maximum effort first heuristic and read the memory. So it's no different from my previous solution, I think. Complexity analysis, time complexity ON2 for every element in the array. We're looking at the next elements to its right, aiming to find a good index. So it's better than 2 to the power of n because it's n times n. Yeah, because for each element, we're looking at some other next element to find a possible good index. Space complexity, 2 times n. First n originates from recursion. Second comes from the usage of the memo table. All right. Dynamic programming bottom up. And this eliminates recursion. Sure. In practice, this achieves better performance as we no longer have to have the method stack overhead and might even benefit from some caching. More importantly, this step opens up possibility for future optimization. The recursion is usually eliminated by trying to reverse the order of the steps from the top-down approach. Yes, as we did here, using the bottom-up DP and using a for loop to go from the from the second to last index to the first index 0, we are eliminating recursion. I mean, although we're calling this subfunction and this subfunction does have a recursion in it, um, but it will probably never be used because the subproblem value will always be available uh, when you do when you accumulate the table or accumulate the memory using a bottom-up approach. So so we will never have to call the recursive function calling itself. Okay, uh, right. This means that if we start from the right of the array, every time we will query a position to our right, that position has already been determined as being good or bad, right? This means we don't need to recurse anymore, and we will always hit the memo table. Yes, good, bad, unknown. Right. So this is, in essence, the same thing that what we're doing. Time complexity, ON2, the same. But in space complexity, um, it's a twice reduction. We're using the memo table, but it's a little bit better than this top-down approach using memory table and recursion. Yeah, because recursion itself takes memory, right? And if you eliminate recursion, you don't need that additional space complexity for remembering where you are in the recursion. Okay, greedy. Really? Are people really using greedy approach? Wow, greedy approach is really much simpler actually. How come? So once we have our code in the bottom-up state, we can make one final important observation. Right, so maybe this is some like problem-specific insight that actually got rid of dynamic programming. Okay, so this is like insight-based observation, insight. From a given position, when we try to see if we can jump to a good position, we only ever use one, the first one. Really? Let's read the sentence again. From a given position, right? A position K, index K, when we try to see if we can jump to a good position, we only ever use one. The first one. Really? see the break statement. Where's the break statement? Where's the break statement? You mean this break statement here? Right? In other words, the leftmost one, really. What does that mean? I'm still not sure. If we keep track of this leftmost good position as a separate variable, we can avoid searching for it in the array. Not only that, but we can stop using the array altogether. Okay, let's just read on to see if it makes sense. Iterating right to left, for each position we check if there's a potential jump that reaches a good index. Current position plus num's current position is greater or equal to leftmost good index. Okay. You know what? This starts to look like that, you know, painted or unpainted heuristic that we had. You're basically saying like if our current position plus the maximum effort, if that is going to get us into the good old painted region, then we're good. If we can reach a good index, then our position is itself good, right? Also, the new good position will be the new leftmost good index. So yeah, this is like the paint spreading process. Uh, but I mean, this is a little bit mind twisting. I mean, I tried that just a, just 1 or 2 hours ago, and it didn't work. So maybe I got something wrong and I almost got there. Is that correct? So you're saying if a current position plus the maximum effort at that current position gets you to a gets you to at least the leftmost good index. Right, because you can cover that, right? Because you can cover. Because if your maximum effort can get you to can get you into the guaranteed most good index, then you can definitely get to the leftmost good index. Right, right, right. This makes sense. If your maximum effort can trespass into a previously found good solution, then you definitely can either use a maximum effort or a lesser effort to reach exactly the previous leftmost good index and continue and pass that goodness down, right? And basically just, yeah, just enjoy that goodness there. Huh. So we almost got there. It's just that we didn't think through thoroughly what is good or not good. So we didn't think it thoroughly through. Right, right. So, okay, so that's something we were missing. And that is like, what, a very good complexity? All right, okay. We almost got it. I mean, I think we got down to approach 3, and we actually did a little bit of a mix. I mean, I did a little bit of a uh did a little bit of improvement by adding a pre-screening on top of approach 3. But then we didn't get to approach 4. I think that's what's missing. And the fact that we're using Python instead of Java is making us look pretty bad in terms of the ranking, maybe. No, they keep a separate ranking for different languages. So I wonder what people are using for this problem using Python. Maybe everybody is using the greedy approach. I don't know, or similarly greedy approaches. So again, if we go back to this thing here, uselessness indices. No, not this one here, but this one here. Actually, even before that, this one here. Well, this is not 100% correct. I mean, maximum effort isn't necessarily good, but you know what's good? If we, right, if we spread this, right, if somehow like a maximum effort, not in this graph. Come on. If somehow, a maximum effort can get into a good index, right? Like if a maximum effort from somewhere can get into the painted area, then we can definitely find, a proper index, a proper effort that arrives at the first element um, in that painted area. So that is basically what we were missing. Uh, right, useless indices. So this is a heuristic that we were using to basically improve our bottom-up dynamic programming a little bit. But then we missed, the very powerful insight into this problem, which is that maximum effort is still good, and if your maximum effort covers a good index, you know, the leftmost good index covers a previous leftmost good index, you can confidently say that the current index is good. Yeah, that's right. That's right. So shall we implement it? We definitely should. Let's just draw a different table with that. Draw a different illustration with that because I definitely want to um, make sure that we remember that because this problem, it's rare that you find something more powerful than dynamic programming. But when you see a problem that um, that is as unique as this, there might actually exist an insight that is better than dynamic programming. And in this problem, it exists. So this is the insight, okay? Uh, we can have subproblems, right? So for example, the first subproblem would be this one. This is going to be like what? Subproblem of n minus 2, right? Uh, yeah, and it could be true, it could be false. And then we can have, if we use a different color, say if we do this, whoops, come on. If we do this will be the subproblem of n minus 3. Also, it could be true or false. It's kind of independent from n minus 2. But we can remember like something called like the left, oops, outline. Let's get 0%, and we could use black here. Yeah, leftmost true subproblem, or we can say leftmost good index, right? So you're gonna basically look at all these indices that you have computed, all these s values you have computed, um, and then you store that as one value, right? Like one value. What value is that? Well, we have to use black for it. You know, we're gonna call it end left good, right? End left good. Uh, and each time when you're doing like the bottom up approach, you update this leftmost good index. And then when you are doing your so-called DP, let's use yellow this time. Say let's just start from any random place, okay? We start from K. And then you just use your whatever, you use your maximum effort, okay? Now you actually use your maximum effort. And then you compare and see if the landing index is greater than this int LG. Because if it is, you need to look no further, because you will always have a lesser effort, or actually the maximum effort. You will always have an effort within your reach to land at the leftmost good index. You're guaranteed to have that, right? So this is the heuristic that we need to test, right? So this is like our version, right? Version 1, yeah, successful version 1, bottom up DP with a smart pre-screening. But this is not optimal. Actually, DP is not optimal. Can you believe that? All right, so we're gonna actually try this, and this is gonna be our version 2 using the powerful insight of leftmost good index and maximum effort. So the only thing we need to change is that we need to keep a memory, right? We need to keep a memory of maximum effort. No, leftmost good index. Where do we store that? We can store it here. Self dot. Actually, we can just store it here. We call it end leftmost good. Yeah. We initialize it as n minus 1. So initialize the leftmost good index as the last index. Right, this is trivial, but we will update that um, repeatedly when we are doing this bottom-up DP. So okay, pre-screening. Let's keep the pre-screening. Keep the structure. Um, and then when we're doing this, actually, this calculation of using maximum effort. So if the maximum effort is greater than not just that, but whoops, no, greater than the end leftmost good index, right? Okay, we're gonna store it as a class property. Uh, and then here we can just say if it's greater than that, then the max, then it's large enough to not, yeah, yeah. We just need to do that. And how do we update? How do we update it? Like each time, each time we store something that's true, we're gonna compare update and leftmost good using this end first. Yeah, we're gonna update the leftmost good index potentially. Um, and then we don't need to and you're telling me we don't need to reduce efforts anymore. Is that what you're telling me? You're telling me we just take our maximum effort. Right. You're telling me we don't need this while loop anymore. Okay, let's just forget about the while loop. If the maximum effort is greater than this, we're going to say return true. But before we return true, we always want to update the index. Um, right. Else return false. Right? Because what you're doing is just you're trying to compare the maximum effort with the leftmost good index in there, and then you don't really need to remember everything else. Like you don't need to. Yeah, the only thing you need to remember is that one index, and you don't even need to remember the you don't even need to remember you don't even need to remember the s. Like this is completely not necessary. Uh, and we're just doing this bottom up, right? Yeah, we're doing this bottom up, and let's forget about the pre-screening, and we just go use that subproblem update, right? And in this subproblem update, we basically look at if the best effort, yeah, we just we just see if the maximal effort can get us past leftmost good good index. That's the only thing. Um, if it does, um, we update the leftmost good index to be the current one, right? Um, update, does it mean like direct override? Because the previous index must be less than ours. Uh, right. So basically it means self.end lg equals to end first here and return true. Else, um, we're going to return this sub as false. Right, we don't need anything here. We don't need anything else here. Okay, let's try it. Solution object has no attribute s. Oh, okay. We have commented it out. Let's just still use it, all right? And it works. And it works. And it works. Cool. This is already better, but we're still using the storage of a what? Of an S dictionary. It's already better, so I'm like kind of like eager to see what will this get us, right? What's the ranking percentage of this new heuristic? 79% better, but memory-wise, we're still not good because we're still using a memory table to store all the values, in the nums array. So is it possible to eliminate the need for this storage? Um, yeah, well, we can because you see now sub doesn't really rely on anything else. We just look at, the truth, and then we just return the truth because after all the for loops, you know, the truth is going to be like S0, and we don't really need this term anymore. Let's try that. Yep, yep, and yep. Right. So we just eliminated this storage, unnecessary, and it's now really compact. This is a very powerful heuristic, and I think with this submission, will be better in terms of memory usage and equally good or even better in runtime. So will probably be above average. Yep. Memory usage is very good. Runtime above average. Let's try it again. Well, it's a different test case, so maybe our memory usage shot up a little bit. So you see, yeah, this is like both above average very well. Okay, so that means we have absorbed most of the knowledge from the solution, and we gradually improved our code to be above average. And I think we can stop here. So now here's today's summary. Well, again, this is another very long video, but we learned actually quite a lot. So we started the problem. Let's take a look at the problem again. We started the problem with, I think, the right approach. We were trying to find a generalization or, let's say, a recursive relationship that we can use to build the backbone for the DP solution. Because we know this is a DP problem, so we were looking for that DP backbone for it. However, uh, it took us some struggle because at first we weren't quite clear about what is a subproblem. Because for the jump game, I mean, the original game, you always start from the first element. And for the subproblem, at some point, I had assumed that, the subproblem, I can start from any point, any index in the subproblem, uh, and as long as I can um, uh, get a true result at the end. So that impression was wrong. Like you cannot define subproblems that way because um, if we are consistent with the original problem, you always start from the first index, and you need to define your subproblems in the same fashion. So your subproblem always starts from the first element or first index in the subproblem as well. So stick with that. Make sure that your original problem and your subproblem have exactly the same structure, uh, except for the fact that your subproblem maybe has few elements in the array than the original problem. Everything else should be exactly 100% the same. That's how you call it a subproblem. So we struggled with that a little bit, and as a result, um, our code um, our code wasn't correct in the first place. And then we moved on to um, a solution that was working by realizing that our generalization of our subproblem was wrong, and we fixed that. And we realized that um, we have to use a pretty expensive calculation that includes trying all the possible jumps uh, at each um, subproblem, right? So you take the first index in every subproblem, and then you start from the maximum effort all the way down to the minimum effort, which is like one one step. Um, and this kind of exhaustive calculating all possible efforts, starting from the first index, really bumped up the time complexity to n squared. Yeah, to n squared. Uh, and that is a problem because there were like tricky test cases in the Leetcode problem, such as this one, where literally you have 10,000 elements in it, and n squared of 10,000, how much is that? It's like 100 million. So that is too much computation, and you'll easily run out of your time limit in your Leetcode. So, this means for an acceptable solution to work, we have to really reduce our time complexity down to at least O of n. Uh, and um, our previous solution was basically a bottom-up approach with that, with searching all the efforts, searching all the efforts for each each initial index of each subproblem, and that really cost us too much time. And then I moved on to find like a simple hack called pre-screening. And what this pre-screening does, I mean, it's not a universal fix. It's just like a hot fix to deliberately, target tricky test cases like this um, by coming up with a way to filter out, cases like this. Um, but since that was like not a general solution, um, if a test case comes more trickier than this, we may still not pass the test. I mean the time limit. So the smart pre-screening, um, so this is like, I mean, still in terms of time complexity, this is still O n squared. And space complexity, I think since we're doing a bottom up, it's O of n. Uh, but but we somehow managed to uh, actually get a pass because uh, for this particular problem, our pre-screening actually reduced the time complexity to O of n. Yeah, so we should probably say that. Um, our smart pre-screening trick uh, managed to bring time complexity to O of n for a special class of test cases, like the tricky case one below. Let me check. Yeah, tricky case one below. Yeah, exactly. But still, the time complexity is O n too, so it's not good. But that is our first successful submission. Um, I mean, it took quite a long time to compute, so it's definitely suboptimal. Uh, and then we looked at the solution. We read the solution all the way down, and we realized that the solution uses dynamic programming from top down, from bottom up. Um, and then those approaches, they still have a time complexity of O n squared, and it's not good, right? If you look at that, um, approach one, approach one is really bad because it's just backtracking, like a tree search. Uh, approach two, dynamic programming top down. It's got a time complexity of O n squared. Uh, and then approach three, dynamic programming bottom up. It's still got a time complexity of O n squared. So we probably still won't get away. We will probably won't. We still probably won't get away with these two versions of dynamic programming for this tricky test case one here. So then from the solution, I realized that there's like a unique insight that we can apply for this problem that is out of the scope of dynamic programming, but it's actually better in terms of efficiency, uh, complexity than dynamic programming. And that insight uh, uh, saved the day. And the insight was that if we remember a crucial piece of information that is the leftmost good index, uh, then we can prove that, if the maximum effort of starting from a certain index can get us past the stored leftmost good index, then we can basically say, hey, the current index that we're testing is also good. So this is like actually exploiting the problem dynamic, and we're basically spreading because the answer is binary, like right, it's either good or bad. We're exploiting this dynamic and getting quick answers without having to build up all the um, tabular values of good or bad from bottom up. So that's as much as I can explain the power of this insight. And then we implemented that, um, and then indeed it became an above average solution. So that wraps up today's episode, and I hope you learned something from it. Um, you probably didn't stick all the way to the end, but I will create time labels, timestamps for this video as usual, so that you can skip the bulk part of it and maybe just jump to the solution, take a look at the code that I have, uh, and then have some takeaways. So thank you guys for watching. I'll see you in the next one.